Welcome back, everyone. So far, we have had a look at the classical linear regression model. We had a look at its two-variable form and also its multivariable form, where it can be extended to the k-variable model, right? And we also had a look at how, if we introduce an additional assumption about normality of the error variable, the disturbance term, we would have the classical normal regression model, and what are the advantages of the additional assumption and so on. Now we are going to have a look at what happens if certain assumptions that we made in the CLRM model are not followed. So we are relaxing certain assumptions. The first assumption that we are going to relax and have a look at is our assumption which says there is no collinearity or linear relationship between the different explanatory variables in our model. If there is some degree of linear relationship or dependency between different x variables of our model, we call it multicollinearity. Okay. This term was originally coined by Ragnar Frisch. He is the same economist who also coined the term macroeconomics for the economics that was forwarded by John Maynard Keynes. Right? So the same Ragnar Frisch also coined the term multicollinearity. Originally, the term is used to denote an exact relationship, linear relationship between some or all of the explanatory variables in our regression model. If you have an exact linear relationship, in terms of an equation, I can write it in this way: lambda 1 x1 plus lambda 2 x2 and so on. Lambda k xk is equal to 0. Which means from this equation you can always show how the variable x2 is an exact function of the combination of variables, linear combination of variables on the right hand side, right? So this is the case of an exact linear relationship between variable x2 and the other variables, x variables. However, we can also use the term multicollinearity in a broader sense, where it refers to less than perfect linear relationships, collinear relationships. If you have less than perfect multicollinearity, your function can be specified as this, that is lambda 1 x1 plus lambda 2 x2 and so on, plus vi is equal to 0. Here this term vi is actually a stochastic or random error term. So the relationship, this would mean that the relationship between x2 and combination of the remaining variables is not exact. It will vary slightly according to the variations in the error term. Here, the last line here shows us how the variable x2 can be expressed as a combination of the other explanatory variables. And if you observe here, this last term is 1 by lambda 2 times vi. So there is an error term involved in this linear relationship, right? So multicollinearity may be perfect or less than perfect. And the fact that there is multicollinearity in a model will have some implications or some effect on the estimators that we are calculating based on the OLS criterion. In this slide, you can actually see a Ballantine view of the multicollinearity problem. Ballantine view is basically, we are using Venn diagrams to get a visual idea about what multicollinearity is. Your figure A is a situation of no multicollinearity. Here the circle y represents variations in dependent variable yi. This circle shows variations in variable x2. The circle here shows variations in the explanatory variable x3. This intersection region represents that part of variations in y which are being explained by variations in x3. Similarly, this portion here, the intersection portion over here, represents the variations in y which are being explained by variations in variable x2. Since your x2 and x3 circles are not intersecting, this is a situation where there is no collinearity between the explanatory variables. Now have a look at the second diagram. Here, the circles x2 and x3 are also intersecting, which means over here we have a portion over here, sorry, one second, yes. Over here we have a portion where the variations in y is being explained solely by variations in x2. This portion over here shows how much of the variations in y is being explained solely by variations in x3. The intersection region over here where the highlighter is the portion of variations in y that is being jointly explained by variations in x2 as well as x3. This is because it is on the intersection of x2 and x3 as well. So for this region, because of the multicollinearity between x2 and x3, we cannot say how much of this region is being explained by variations in x2 and how much of it is being explained by variations in x3. All we can say is that both jointly explain this much of the variations in dependent variable y. The lower three diagrams show instances of greater and greater multicollinearity. If you look at this last diagram here, you can see that there is high collinearity between x2 and x3. So a large portion of the variations in y are being explained jointly by variations in x2 and x3. In this entire shaded region, we cannot isolate and say this much of the variations are due to x2 and this much of the variations are due to changes in x3. In this entire shaded region, all we can say is that x2 and x3 together explain this much of the variations in dependent variable y. So that is our main problem also when we have multicollinearity in our sample. We are unable to say how much of changes in y are due to the influence of one variable, individual variable alone. Every time you are in this region, all we can say is that the variations here are being jointly explained by variations in the explanatory variables x2 and x3. We can't say that half of it is due to changes in x2 and half of it is due to changes in x3, right? And that becomes the problem of multicollinearity. One technical point to be noted is multicollinearity only considers linear relationships. Okay, so as such, if we have non-linear relationships, such as over here, you can see over here, yi is equal to beta naught plus beta 1 xi plus beta 2 xi square plus beta 3 xi cube. So the explanatory variables are powers of the same variable xi. Since these variables are not exactly linearly related, we are not violating the assumption of no multicollinearity. Okay, so theoretically, there is no assumption violation happening here. But practically, if you run this model and you run for the relation collinearity between xi square and xi cube, you will notice that it shows up as being highly correlated. Not perfect, because it's not a perfectly linear relationship, but still xi square and xi cube will show high correlations if you test it statistically. Okay, but again, technically speaking, a model such as this is not violating our assumption of no multicollinearity, because that only talks about linear relationship, whereas xi square, xi cube are non-linearly related variables. So let's have a quick look at what are the sources of multicollinearity that can enter the sample. The first important source is the data collection method that has been employed. If you're sampling over a very limited range of values taken by the regressors or the x variables in the population, you can often see that the x variables that we have chosen are linearly related, or they have high correlation between each other. Another source is when the constraint on the model, when there are constraints on the model or in the population that is being sampled. This can be understood by the use of with this example. Say we are studying the determinants of electricity, the consumption expenditure of a family, and our explanatory variables are electricity consumption on say we are trying to find the determinants of electricity consumption. Our two dependent variables are income and the size of the house, right? As you can see, in most of the population, families with higher incomes generally will tend to have families with larger homes, and similarly families with lower incomes will tend to be the families with smaller house sizes. So the model per se itself may sometimes be such, the constraints on the model itself might be such that our x variables are highly correlated. Sometimes the nature of model specification can lead to high multicollinearity. The model that I mentioned in the last slide, where your yi is beta 1 plus beta 2 times xi plus beta 3 times xi square plus beta 3 times xi cube. In that model, when we are adding polynomial terms, these terms xi square, xi cube and so on, they are called the polynomial terms. When we add polynomial terms to the regression model, and especially in the situation where the range in which the x variable varies is very small, automatically multicollinearity happens. If you are trying to estimate the long run average cost function of different firms, you will end up using xi square and xi cube as your explanatory variables, because the theory demands so. So this model specification might be the reason or the source of multicollinearity. Another very important source of multicollinearity is an overdetermined model. By that I mean that when you have more explanatory variables than you have the number of observations, then there will be very high multicollinearity between your x variables. In practical situations, especially in the field of medical research, this happens quite a bit, because you have a small number of patients on whom, say, the vaccine is being tested, the COVID vaccine is being tested, but you have information regarding a large number of x variables. So you are talking about effectiveness of the COVID vaccine, and you have a large number of explanatory variables such as age, presence of heart ailments, presence of diabetes, presence of any gastrointestinal problems and so on. So you have large number of variables, data about large number of variables, but you have a very small number of patients. So what happens? Your number of observations, if it is less than the number of explanatory variables, you will not be able to estimate the model, and there will be high multicollinearity in your model. An additional reason could be when, especially in the case of time series data, it is possible that the explanatory variables that you have chosen follow the same trend. So again, understand this on the basis of an example. If you're trying to determine your y variable is consumption expenditure, you can think of 3 explanatory variables in time series. You can think of income, wealth and the population as 3 reasonable explanatory variables in your consumption expenditure model. However, in time series, income, wealth and population, all of these seem to have the same trend, that is, they increase at almost the same rate over time. So automatically these 3 x variables will show up as being extremely collinear. So the fact that this is time series data where they share the same trend, that can be a source of multicollinearity among